of interest is commutative algebra, quantum algebra, free probability theory, and subfactor theory and planar graphs. And he rendered his service as assistant professor at University of Kansas Lawrence and visiting professor at University of Nebraska and visiting scientist at ISI Bangalore. And he has around 28 years of teaching and research experience in the field of mathematics. And now he is working as a professor at IMSC Chennai. And I thank him for accepting our invitation to deliver the lecture. Now I welcome Professor Vijay Kodiyalam, sir, to deliver his lecture. Welcome, sir.
Thank you. Am I audible?
You are audible, sir.
Okay, fine. So let me start sharing screen first because I'll need to write on the screen. Okay, so is my screen visible?
No, sir.
No, sir.
No, not yet.
Not visible.
Not visible. Okay.
Yes, it's coming.
It's visible, sir.
Yeah.
Okay, fine. Yeah. So thank you for the introduction. So what I'm going to do is some topics in ring theory. So let's see. So I'm going to deal with some topics in ring theory in this series of lectures, 6 lectures. So today, what I'm going to deal with is the Chinese remainder theorem, Lagrange interpolation, and applications. So that's the topic for today. Chinese remainder theorem and its applications, which include Lagrange interpolation. So let's begin with a simple problem. So here's the problem. So the first problem that we want to deal with is an easy problem. So it says find a positive integer n such that on division by 2 leaves a remainder of 1. On division by 3 leaves a remainder of 2. So on and so forth. On division by 10 leaves a remainder of 9. So we want to consider problems of this kind. So we want to find integers satisfying various conditions of this kind. That is, on division by something leaves some particular remainder. So this is one specific example of such a problem. This problem, as it turns out, is quite easy to solve. It's easy to solve because there is a certain pattern in these remainders. So if on division by 2 it leaves one remainder, then when you add 1 to that integer, it's divisible by 2. It's also divisible by 3. It's also divisible by 4. And so on and so forth, it's divisible by 10. So clearly, if n is that integer, n plus 1 is divisible by all 2, 3, 4 up to 10. So if you want to find the smallest number which is divisible by 2, 3, 4 up to 10, then of course you have to take the LCM of all these numbers. So n plus 1 equals the LCM of 2 up to 10. And this you can calculate is some 2520. That's n plus 1. What we are looking for is n. So n equals 2590. So this number, if you take, On division by 2, it will leave remainder of 1. On division by 3, it will leave remainder of 2, so on and so forth. Okay, so but this was a very special problem because the remainders had a certain pattern. What do we do when there is no such pattern in the remainder? So rather than dealing with 10 of them, let me just start with 2. So let's consider the following problem. Okay. So find. So now let me change notation. Let me call it x. Find x such that x is congruent to A mod m and x is congruent to B mod m. So here we are given these integers a, b and mn. So you're given all of this and you want to find the x which satisfies these conditions, whether such an x exists, and if it exists, what are all such x's? Questions of this kind. So it turns out that such an x, so it's a fact. We'll prove this shortly. Such an x always exists if m and n are co-prime. That is, their GCD is 1. i.e., this notation is for the GCD. The bracket mn notation is for the GCD. So such an x always exists when m and n have GCD 1. So let us try and see why this is the case. So it's not hard to see that this is correct. So let's try and understand why this is correct. So one thing that you will have to know about co-prime integers is a very fundamental fact about co-prime integers is that some linear combination of those two is 1. So fact, if m and n are co-prime, if the GCD of m and n is 1, then there exist integers. Let's see. So a and b, such that, let's not call it a and b. Let's call it, say, p and q, such that pm plus qn is 1. In fact, more generally, if the GCD of m and n is some d, then there exists p and q such that pm plus qn is d. So let's assume first that we are able to find such p and q. So assume, and I'll discuss this in a second, how to find it. So assume that we can find such p and q. So I'm given m and n, which are co-prime, and I'm able to find p and q such that pm plus qn is 1. Once I do that, how do I solve this problem? So we have to notice some things about pm and qn. So consider the integer pm. What remainders does this leave on division by m and n? So clearly, on division by m, it leaves 0 remainder. It's divisible by m. But pm is also equal to 1 minus qn. So on division by n, that means it's 1 away from a multiple of n. So on division by n, it leaves 1 remainder. So pm satisfies these two conditions. On dividing by m, it leaves 0 remainder, and on division by n, it leaves 1 remainder. Similarly, the integer qn leaves remainder 0 on division by n and 1 on division by m. Now we can use this to solve the problem. So we have found two integers, one of which leaves a remainder 0 on division by m and remainder 1 on division by n, and the other which does the opposite, leaves remainder 0 on division by n and 1 on division by n. So what we can do is, so now given a and b, let us consider x. So what do we want x to satisfy? It must leave remainder a on division by m and b on division by n. So let's just consider a linear combination of this pm and qn. So it's a times one of them plus b times the other of them. So it must leave remainder a on division by m. So here you put in the one that leaves a remainder of 1 on division by n. So that is qn and b times pn. So let's consider this. Consider this integer, which is aqn plus bpn. So this x satisfies both conditions. This x satisfies x is congruent to a mod m and x is congruent to b mod n. We can check this. That means on division by m, it should leave a remainder of a. On division by n, it should leave a remainder of b. Because if you divide by m, this part is divisible by m. This leaves a remainder of 1 on division by m. So if you multiply with a, then it will leave a remainder of a on division by m. Similarly, it will satisfy the other condition. So this essentially solves this problem. Provided, so we have solved it. We have solved the problem. Provided we can find P and Q such that Pm plus Qn is 1. Now this problem, so why is it called the Chinese remainder theorem? So this problem, so around the 3rd century AD, so it appears in a book, in a Chinese textbook by some Chinese mathematician. I don't remember the name, but this does that textbook has various examples of this question and various solutions for these examples. A little later, around 5th century AD, so in the work of Aryabhata, there is an algorithm. There is a method for solving this question in general. In his book Aryabhatiya, he has a solution for this question in general. Okay. So, and so now we have, I have presented one such solution to you. So we still have to solve this question. We still have to do this problem of finding P and Q such that Pm plus Qn is 1. And for this, we will appeal to what is called the Generalized Euclidean algorithm. So what does this Generalized Euclidean algorithm do? So I will tell you what its input is and what its output is, and then I'll describe the algorithm. So the input for this algorithm is a pair of integers. Let's say positive integers, m and n. And the output is the GCD of m and n together with P and Q such that Pm plus Qn is D. So this is exactly what we want to do. We want to take two integers m and n, and we want to write the GCD as Pm plus Qn for some integers Pq. We want to find those integers. We are especially interested in this when m and n are co-prime, in which case D is 1. So we want to write 1 as a combination of Pm plus Qn. So how does this algorithm go? So let me describe that. Rather than writing this algorithm formally, I'll work out one example. So suppose m is 30, m is say 45, n is 13. Okay, 45 and 13, these are certainly co-prime. They don't have any common factors. So their GCD is 1. So what we would like to do is we want to write 1 as a combination of 45 and 13. P times 45 plus Q times 13 must be 1. We want to find P and Q. This is what we want to do. So we arrange this. So it's convenient to arrange this work in the form of a table. So we first write down. So it's a sort of. Okay. So first write down 45, 10, and 13, 0. And here I'll make another column called the quotient column. First quotient column is empty. So this is how the algorithm starts. You write down 45, 10, 13, 1, and then we are going to increase this table downwards. We are going to build a table. So how do we build this table? So each time we will first find out what the quotient is. So what is the quotient? The quotient is you have 45 and 13. You divide 45 by 13 and write down the quotient. Forget, don't worry about the remainder for now. Just write the quotient. So 13 goes 3 times in 45. 13 3s are 39. And that leaves a remainder of 6. Never mind that. Okay. Once you write down the quotient, we can fill in the next line of the table. So the next line of the table goes as follows. You take this vector 45, 10 and take this vector 13, 1 and subtract 3 times this vector from the top vector. So 45, 10 minus 3 times 13, 1. That is going to be the next line. So 45 minus 3 times 13 is 6. 1 minus 3 times 0 is 1. 0 minus 3 times 1 is minus 3. So this is my next line. Then again, I fill the quotient. So the quotient is between 6 and 13. How many times 6 goes in 13? 6 goes 2 times 12. So write down that. Then we can go to the next step of the table. So in the next step of the table, it is the vector 13, 1 minus 2 times the vector 6, 1 minus 3. So 13 minus 2 times 6 is 1. 0 minus 2 times 1 is minus 2. And 1 minus 2 times minus 3 is 7. So we get the next thing, which is 1 minus 2, 7. So we want to proceed until something happens. So I tell you what's going to happen. It's going to happen at the next stage. So this time the quotient is 6. So the quotient here is we divide 6 by 1 and write down what the quotient is. There's no remainder, doesn't matter. We're just worried about the quotient in this. In this last column is just the quotient column. Then what do? I take the vector 6, 1 minus 3 and subtract 6 times the vector 1 minus 2, 7 from it and see what happens. 6 minus 6 times 1 is 0. 1 minus 6 times minus 2 is 13. Minus 3 minus 6 times minus 7 is minus 45. So I get to this column. Now do this procedure until the first entry becomes 0. So repeat procedure. Until the first entry is 0. And we have reached that stage. This is the first entry, 0 now. So you have to keep doing this until you get to 0. And then when you get to 0, then the answer. So the GCD is then the previous first entry. Here it is 1. So the GCD is 1, and further it is expressed as Pm plus Qn, where P and Q are the second and third entries of that column, of that row. So in this case, minus 2 and 7. So 1 equals minus 2 times M45 plus 7 times 30. And that's correct. 45 times 2 is 90, minus 90 plus 13 times 7 is 91. 1 equals. So we have found out this is Pm plus Qm equals the GCD D. So this procedure is called the generalized Euclidean algorithm. I don't want to get into a proof of this. It's not very hard to prove, but this is the procedure, right? So the generalized Euclidean algorithm will help us find PQ such that Pm plus Qn equals 1, and thereby it helps us to solve this general problem of finding x such that x is congruent to A mod m and x is congruent to B mod m. So simultaneous congruences you want to solve with respect to moduli which are co-prime to each other. If m and n are co-prime to each other, then we can always solve this problem. This is the classical Chinese remainder theorem. Next, let's get to something which doesn't seem to be related at first sight, but actually it is essentially the same thing, and that is called Lagrange Interpolation. So here the setting is slightly different. So we are not working over integers, we are working over a polynomial ring in one variable. So let K be a field. Let's say Q or R or complex numbers, something like that. So K is some field, and consider the polynomial ring Kx. So this is polynomials in one variable x with coefficients in K. Okay, so this is where all the action is going to happen. And what's the problem? So the problem is the following. It's a problem actually which is quite useful in applications. So we are given various, so let me draw it in terms of a graph. You're given some points x1, x2, x3, xk, and you're given points with these x coordinates. So you're given one x1, y1. Then you're given some point x2, y2. Then you're given some point x3, y3. So on and so forth. You're given some point xk, yk. So you're given all these points. Now what you would like is a polynomial which goes through all of these. The graph of the polynomial should go through all of these points. So maybe something like this. So given points x1, y1, x2, y2, xk, yk, where of course all the x's have to be distinct. But the xi's are all different. You cannot have a graph which goes through these 2 points one above the other, right? That won't be the graph of a function, right? So given points x1, y1 up to xk, yk, where the xi's are all different, we seek a polynomial say fx whose graph goes through all these points. That's a very natural question to ask. So how do we find such a polynomial? And not only we want a polynomial whose graph goes through all these points. In the previous case, we said we wanted the least one, right? When we wanted the least integer n, which satisfied those conditions. Similarly, we want a polynomial, in this case, of smallest degree. So we want a polynomial of smallest degree satisfying these conditions, going through these points. So how do we do this? The situation is, if you think about it a little bit, we will see that there is an analogy between what we did earlier and what we are going to do now. So let's see how to do this. So first, let us try to understand how many conditions. There are k conditions, right? So it has to go through x1, y1 is one condition. It has to go through x2, y2 is one condition. So on up to xk, yk. So there are k given conditions. So what polynomial would you expect to satisfy? What degree polynomial would you expect will satisfy all of these things? So a polynomial of degree 2 has three coefficients, right? Ax squared plus bx plus c. That's a quadratic polynomial. A polynomial of degree 3 will have four coefficients. A polynomial of degree k minus 1 will have k coefficients. So maybe we can adjust the k coefficients of a polynomial of degree k minus 1 and satisfy all these conditions. So this is a guess. So the first we begin with the guess. So perhaps we can adjust the k coefficients. Is there a question? Okay. So perhaps we can adjust the k coefficients of a degree k minus 1 polynomial so as to satisfy all these conditions. So we'll try this and see if it is possible. Okay, so what is a general degree k minus 1 polynomial? So that is, assume that f of x is a naught plus a1x plus a2x square up to k minus 1, ak minus 1 x to the k minus 1. So let us consider an fx of this form, a polynomial in one variable x of this form, and let us try to solve for the conditions. We want a naught, a1, a2 up to ak minus 1. So we want one second, I think, just give me a second. I think it's stuck. 1 second. Okay, so we want an fx such that it's not writing. Sorry, it's not writing. Just give me a second. Just give me a second. I'll be back in a second.
Okay, sir.
Okay, is the screen visible?
Yes,
Yes,
sir.
sir.
It's visible,
Yes,
sir.
Am I audible? Yeah. Okay, fine. So, so we want to, what are the conditions? So we want f of x1 to be y1, f of x2 to be y2, up to f of xk equals yk. So these are the conditions that we want satisfied. So want to get a naught up to ak minus 1 such that all these conditions hold. So let's write down f of x1 equals y1. What does that mean? So that means a naught plus a1 x1 plus a1 a2 x1 squared up to ak minus 1 x1 to the k minus 1 equals y1. Then a naught plus a1 x2 plus a2 x2 squared up to ak minus 1 x2 to the k minus 1 equals y2. And so on and so forth up to the kth equation, which is a naught plus a1 xk plus a2 xk squared up to ak minus 1 xk to the k minus 1 is yk. So this is the set of equations that we have to solve. Now please remember that the variables here are not the x's, the variables are the a's. The x's are what we know, the x's and y's are what we know, right? So this can be written as a matrix equation. So we will write it as a matrix. So write this as a matrix equation. So what is the matrix equation? So the matrix equation looks like this. So it is 1 x1 squared up to x1 to the k minus 1. Then 1 x2 squared up to x2 to the k minus 1. So on up to 1 xk squared xk to the k minus 1. This is the coefficient matrix times a naught a1 up to ak minus 1 equals y1 y2 up to yk. So written as a matrix equation, this is how it looks. So again, let me remind you, the variables are a naught up to ak minus 1. That is what we are trying to solve for. And the x's and y's are known. So you know this matrix, you know this vector, you want to find this one. That's what you want to find. So, and we also know when does this have a solution. It has a solution if you can invert this matrix. So this is a k by k matrix. And if this matrix is invertible, then it will have a solution. So this can be solved if this matrix is invertible. And we know how to check for invertibility of a matrix. We can calculate the determinant and check whether the determinant is 0 or non-zero. If it is non-zero, then we know that the matrix is invertible. So we want to calculate, we want to check if the determinant of this matrix is non-zero. And this, of course, we are all aware that this is the so-called van der Waals determinant. Okay, so the determinant. So here is a proposition or whatever it is. So the proposition is this determinant, which is 1 x1 of x1 to the k minus 1, 1 x2 up to x2 to the k minus 1, 1 xk to xk to the k minus 1. This determinant can be explicitly calculated, and it's the product over all j bigger than I of xj minus xi. This is the proposition. So this proposition tells you what the determinant of such a matrix is. In particular, conclusion is if x1 up to xk are all distinct, then the determinant is not zero. Because all these terms, xj minus xi, if they are all distinct, none of these terms are zero. So the product also is not zero. Hence the determinant is not zero. Okay. So once we have this proposition, once we have this is the so-called the van der Waals determinant. So if you know this proposition, then we know that the matrix is invertible. And once this matrix is invertible, if you, no matter what y1 up to yk is given, you can solve this equation and get a0 up to ak minus 1, which means you can always find a polynomial of degree k minus 1 that will go through any given k points. That's what the conclusion will be, right? And that's called Lagrange interpolation. But Lagrange interpolation actually doesn't do it quite using van der Waals determinant. There's a much neater and nicer way of doing this, more suited to calculations. So I'll come to that in a second. But before I go there, let's try and understand the proof of this proposition. This proposition is important, right? This van der Waals determinant occurs in all kinds of places, right? It will come up in various situations. So understanding why this expression is correct, why is the determinant of this van der Waals matrix the product of all the xj minus xi's where j is bigger than I. So the proof of the proposition is by induction on k, right? So first let's do the basis case. Say case 2. So what's the determinant? It's 1 x1, 1 x2. And the determinant, if you calculate, it's just x2 minus x1. Right? So it's correct. So the basis case is correct. So inductive step. So assume true. Assume result is true for k minus 1 sized matrices. And will show for k size. Using properties of determinants. Okay. So So I have to start, I want to calculate this determinant. So I want to use properties of the determinant to show this. One of the properties of determinants is if you subtract a multiple of one row from another row, then the determinant does not change. So what I would like to do is, I want to make all these entries 0. Right? By subtracting the first row from the second, third, fourth up to the kth row, I want to make all of these entries 0. So let us call this, let D be the determinant. So let D be this number, which is the determinant of this matrix. I want to calculate D by first making all the entries in the first column 0, except for, of course, the 1, 1 entry. So using row operations, we see that D is also the determinant of the following matrix. So what is that following matrix? The following matrix, we have 1, x1, x1 squared, up to x1 to the k minus 1. Right? And you want to make all of these 0. So here you will have x2 minus x1, x3 minus x1, so on up to xk minus x1. Then you have x2 squared minus x1 squared, x2 squared minus x3 squared, x2 squared minus x1 squared up to xk squared minus x1 squared, and so on and so forth. It goes up to x1, x2 to the k minus 1, minus x1 to the k minus 1, x3 to the k minus 1, minus x1 to the k minus 1, xk to the k minus 1, minus x1 to the k minus 1. So by row operations, we get this matrix, right? Now we want to calculate the determinant of this matrix. Now what is nice about this matrix is, so in this row, all the entries are divisible by x2 minus x1. Right? In this row, in the next row, all the entries are divisible by x3 minus x1. And in this, everything is divisible by xk minus x1. So D is the determinant of this matrix. So if you start expanding along the first column, you will get 1 times the determinant of this smaller matrix. And all the other things, there's no other thing to expand if you are expanding along the first column. So expand along first column. Along first column. To get D equals x2 minus x1, x2 square minus x1 square, up to x2 to the k minus 1 minus x1 to the k minus 1, so on and so forth, xk minus x1, xk squared minus x1 squared, xk to the k minus 1 minus x1 to the k minus 1. Okay. So now, as I said, you can take out an x2 minus x1 common from this. You can take out an xk minus x1 common from this. You can take out lots of commons. And what will you get? You will get a matrix of this kind. 1, 1, 1. All of these are 1. Right? Here you will get x2 plus x1, x3 plus x1, xk plus x1. Then here you will get x2 square plus x1 x2 plus x1 square, x3 squared plus x1 x3 plus x1 squared, so on up to xk squared plus x1 xk plus xk squared, and so on and so forth until that last term which is if I take x2 to the k minus 1 minus x1 to the k minus 1 divided by x2 minus x1, I'll get x2 to the k minus 2 plus x2 to the k minus 2 x1 up to x1 power k minus 2. So these are just some calculations which you can easily do. Xk to the k minus 2 plus xk to the k minus 2 x1 x1 to the k minus 2. Times whatever you have removed. What have you removed? You have removed one x2 minus x1, and then you removed an x3 minus x1 from the next row up to xk minus x1 from the last row. Okay, so this still doesn't look like a van der Waals, look like a smaller van der Waals for us to be able to apply induction, but we can do it. So what you do is, first of all, you have this first column of ones, right? From the first column of ones, you subtract x1 times the first column from the second. Then all these x1s will go away. Then you subtract x1 squared times the first column from the third column. You subtract x1 squared times the first column. So all of these will go away. And similarly, all of these will go away. All the x1s, just the plain x1 terms will go away. Now, what about this x1, x2 plus x1, x3 plus x1, xk? If you subtract x1 times the second column from the third, then all of these will go away. Right? If you subtract x1 times, let me see. Yeah. So in this, so now you see that your second column is just x2 up to xk, third column is just x2 squared up to xk squared, and so on. So proceed in this manner. Actually, you have to do it carefully by induction. Proceed in this manner to show that D equals x2 minus x1, x3 minus x1 up to xk minus x1 times the following determinant. And the following determinant is just a smaller van der Waals. You just get 1, 1, 1, 1. x2, x3 up to xk, x2 squared, x3 squared up to xk squared. Up to the last one will be, only these will be left. All the others would have gone. x2 to the k minus 2, x3 to the k minus 2, up to xk to the k minus 2. And now I claim we are done by induction. We know how to calculate the determinant of this matrix. It's a k minus 1 sized van der Waals. Now, I've gone a little fast through this. If you haven't understood the proof, I suggest you go through this, write it again clearly. Try that. Okay, so try. So if you don't understand, try the k equals 4 case to understand. So 3 will be too small. You try the k equal to 4 case to understand how this proof works and how it shows that the product is x4 minus x1, x3 minus x1, x2 minus x1, etc., etc., right? So try the 4th case to understand the proof. Okay, so once we have this van der Waals, as I said, this van der Waals is the main thing in doing Lagrange interpolation, and it will show that we can solve provided this matrix is invertible, and that matrix will be invertible if the van der Waals determinant is non-zero, and it is non-zero because all the x's are distinct. But this is a rather inefficient way of that's an inefficient way of doing Lagrange interpolation. So here is a more efficient procedure for doing interpolation. And this is the standard procedure. More efficient way to do interpolation. And the more efficient way relies on the following thing. See, what did we do when we were trying to calculate when we were trying to calculate x is congruent to A mod M and x is congruent to B mod N, we first found out something which was 1 mod M and 0 mod N, and something which was 0 mod M and 1 mod N. And then we could combine it with A and B and get an answer. So that's the same kind of idea we are going to use. So more efficient way to do interpolation is try to find polynomials of degree k minus 1 such that let's give these polynomials names, right? So P1, P2 up to Pk, right? Let us try to find polynomials, k different polynomials, all of them of degree k minus 1, such that the following conditions hold, such that at x1, P1 is 1, and at x2 it is 0 up to xk. P1 is 0. So I want to find a polynomial which is 1 at x1 and 0 at x2 up to xk. Then I want my polynomial P2 to be 0 at x1, 1 at x2, and all other points 0. So on and so forth. Pk should be 0 at x1, 0 up to xk minus 1, but pk of xk should be 1. Suppose we can find such polynomials, right? If we find polynomials p1 up to pk of degree k minus 1, such that pi is 1 at xi and 0 at all the other x's, at xj where j is not equal to 1. Then we can easily solve this Lagrange interpolation problem. Then our required polynomial will be f of x equals y1 p1x plus y2 p2x up to yk pk of x. Because you can see what value does it take at x1? All these things will become 0 because P2 at x1 is 0, P3 at x1 is 0, Pk at x1 is 0. So the only thing it will take is this at x1, but this one at x1, P1 of x1 is 1. So it's y1 times 1. So at x1, fx takes value y1. So then clearly f of x1 is y1. Similarly, f of x2 is y2 and f of xk is yk. And further, the degree of f is less than or equal to k minus 1. Because all these p's, if we have found the p's of all of degree at most k minus 1, then the degree of f is also at most k minus 1. It's just a linear combination of the p1, p2 up to pk. So how do you find a polynomial? How do you find these p1 up to pk? So how to find p1, p2 up to pk? And that is not hard to do, right? You want a polynomial which has to be 0 at x2, x3, x4 and all. So it better be divisible by x minus x2, x minus x3, x minus x4, so on. So just consider x minus x2, x minus x3 up to x minus xk. Let's consider this polynomial. This clearly vanishes. So this is 0 at x2, at x3, up to at xk. So this is 0 at all. Whenever you substitute a capital X to be either x2 or x3 or x4 up to xk, this polynomial becomes 0. And at x1, it takes the value x1 minus x2 into x1 minus x3 up to x1 minus xk, which is a non-zero value because x1 is not equal to x2, x3, anything up to xk. The x's are all distinct. So this gives you a non-zero value. And so simply you can take my p1 of x. So p1 of x is the product of all of these divided by this number. The number is x1 minus x2, x1 minus x3, up to x1 minus x2. So you can define this to be P1 of x. Then this P1 of x satisfies all the properties we want. Similarly, if you want to do P2 of x, so it is x minus x1, x minus x3, leave the 2 out, up to x minus xk, divided by x2 minus x1, x2 minus x3, to x2 minus x3. And so we have finished. We have solved the Lagrange interpolation problem. Notice some similarity, right? So these solve the Lagrange interpolation problem. So what is the similarity? So what is the similarity between what we did first, the Chinese remainder theorem, and this, what we have done now, which is the Lagrange interpolation? What exactly is the similarity? There is, you can see in the solution, there is some similarity. We're trying to find something which is 1 in one condition and 0 on several other conditions. And that is how we used, that's the same technique we used to do both the Chinese remainder theorem and the Lagrange interpolation. Okay, so to know the similarity, I'll have to do a little bit of general ring theory. So let's begin with some commutative algebra. Okay. So let's begin with commutative rings. So if we all know what a ring is, right? So a ring R is a set with two operations plus and dot, such that satisfying some conditions. So first, R is an abelian group with respect to plus. Second, that, for example, multiplication. So dot. So we are dealing only with commutative rings. So dot is commutative, associative, and 3 dot distributes over plus. I.e. A dot B plus C, A dot B plus A dot C. And further, I want to impose the condition that commutative rings with 1, with identity. So there exists a 1 in R, which is a multiplicative identity. So 1 dot A is A for all A. Right. So anyway, so this some, so we all are familiar with rings, right? So the only thing I want to point out is, in whatever I am lecturing, I will always consider commutative rings with 1, right? I will not consider rings without identity. All rings that I consider will be commutative and will have an identity element 1. Now there is one ring which is very special among these. So this includes, rings include the 0 ring. This 0 ring is a ring with only one element, which is 0, right? And that's this identity element of that abelian group. The identity 1 is also 0, right? Here 1 equals 0. and it's the only ring where 1 is 0. In all other rings, 1 and 0 will be two different elements. The reason I'm mentioning this is because this is the convention that is usually followed when we talk about commutative rings with identity. The 0 ring is also considered as an example, as a somewhat special example, but it is included. Anyway, you can ignore this comment if you don't want. Okay, so whenever we make a definition, right, it's not enough to deal with it abstractly. So we need to have several concrete examples of these things, right? So I've defined a commutative ring with identity. Now I want a wide variety of examples of commutative rings with identity, so that whenever we prove something or whenever we are trying to study something, we need to look at those examples and see what those concepts mean in these particular examples. So I will give you a bunch of examples of commutative rings with identity, and these rings will be most important for us going forward. Okay, so here are some examples. So the simplest kind of commutative rings with identity are fields, with which we are quite familiar. For example, the rational numbers, real numbers, complex numbers, and the finite fields Zp, P prime. So these are the simplest examples of rings. Why do I say that fields are the simplest examples of rings? Why not, for example, the ring of integers? That's a very simple example of a ring. But in terms of ring theory, the ring of integers is vastly more complicated than a field is, because in ring theory, what is very important is what are the ideals? How is the ideal structure of these things? Z has a lot of ideals. Fields have, on the other hand, only two ideals, which is the zero ideal and the entire thing. Right? Fields are the simplest in terms of rings because they have very few ideals. Fields have only two ideals. So, zero and everything. Okay, so these are the simplest examples. Then moving forward, the next slightly more complicated example is something like Z. Right? The ring of integers. This is a very fundamental example in rings. Or you have something like Kx, polynomial ring in one variable. K is a field. But why should we restrict ourselves to polynomial rings in one variable? We can consider polynomial rings in many variables. So Kx1 up to xn, where K is a field. K need not be a field also, but let's restrict ourselves to the case polynomial rings over a field in one variables or in several variables. So these are examples which arise in algebraic geometry. Then there are examples that arise in number theory. So there are two sources of rings or two sources of commutative rings or commutative algebra. One is number theory and another is algebraic geometry. So in algebraic geometry, the rings that are important are rings of this kind. Over a field, polynomial ring in several variables over a field and various of its quotient rings. I'll get to that shortly. In number theory, on the other hand, the rings that are important are the rings which lie between Q and some field extension of Q. For example, rings like Z adjoint I. Right? So this is a subring of the field of complex numbers, right? Or we could take Z adjoint omega, where omega is a cube root of unity. So, for example, I could take the cube root half plus I root 3 by 2. Right? So these are all examples of rings. So these are the examples of rings I would like to keep in mind while discussing ring theory. In particular, I want to concentrate in this. I don't want to take Kx1 up to xn. I want to particularly look at the case of two variables, Kxy. This is much more complicated than a polynomial ring in one variable, kx, right? So we know various properties of these rings. So what properties do we know? So let me review a few things. For example, we know that Z is a principal ideal domain. That means every ideal is generated by one element. Kx also is a PID, also a principal ideal domain. And it turns out that Zi also is a PID. Z omega also as a PID. You may not be very familiar with why Z omega as a PID. It turns out that all of these theorems are true because all of these things form a class of rings called Euclidean domains, right? So all of these are Euclidean domains. So Euclidean domains are where the Euclidean algorithm holds for some particular choice of function. So maybe I'll define it if needed, but for now we won't need it. So all of these are PIDs. On the other hand, KXY is a much more interesting ring. KXY is definitely not a PID. Not every ideal in this is generated by one element. So we'll get to ideals and what we can do with ideals in a bit. Okay. Okay, fine. I think this might be a good place to stop for today. So I will continue on Saturday. So is that okay? Is that fine? Can I stop now?
Okay, sir.
Yes, sir. Okay, sir.
But before I stop, let me just ask, are there any questions on what we have done so far? So I strongly encourage you to ask questions. Even while I'm speaking in the middle also is okay, but particularly at the end, please do ask. If anything is not clear, I can clarify it the next time. Or if something else, any other questions or comments, whatever it is, please feel free. I see, so there's one chat thing, let me see.
So this question from YouTube live.
Is the set of irrationals, is it?
Yes, sir.
Yeah, no. The set of irrationals definitely is not a field because it's not even closed under plus, right? The sum of two irrationals is not always an irrational number. Root 2 is an irrational, minus root 2 is an irrational, but the sum is 0, right? Which is a rational number. So certainly not. It's not even a group.
Okay, sir. Thank you, sir.
Okay. Any other questions?
So the Lagrange interpolation, please go to the
Yes.
slides. In that slide.
Lagrange interpolation?
Please go to that slide, sir.
Okay.
Using Chinese remainder theorem, you solve the P1 of x1 equal to 1 congruent modulo.
Oh no, I haven't used the Chinese remainder theorem yet. So I have not yet done Lagrange interpolation using Chinese remainder theorem. So far, I have just done using this Vandermonde.
Okay.
I'm coming to that one. I'm coming to that one. I'll do that the next time.
Okay.
So I haven't used the Chinese remainder theorem to do Lagrange interpolation yet. I will get to that soon.
Okay.
Any other questions?
Can
So shall I
we
stop?
extend?
Yeah.
Is it possible we can extend to polynomial two variable?
What do we want to extend?
So for Lagrange theorem, we can approximate a polynomial, a single variable.
Yes.
If it suppose we have polynomial in two variable, can you have any method to?
Yes. There are methods where suppose you're given, for example, suppose you're in two variables. Suppose you're given points x1, y1, z1, right? So you're given various points x1, y1, z1, x2, y2, z2. You want to find a polynomial such that the graph of that goes through all of these points. It is possible to do that. It's possible to do that. But I'm only doing this one variable case to show the close relationship with the Chinese remainder theorem. And I want to do a general version of the Chinese remainder theorem, which will imply both of the things that we did. That's what I'm planning to do the next time.
Okay.
Any other questions? Okay. So if not, then we can wait. Yes. What is the thing?
Sir, one more question from you.
Yeah. What is the guarantee for the polynomial to be the least degree? Okay, that's a good question. Okay. The guarantee for the polynomial to be of the least degree is because, in fact, what we will show, okay, if we do it carefully, we will see that that polynomial which I have constructed is the unique one of degree less than or equal to k minus 1, which works. There is no other polynomial of degree less than or equal to k minus 1 that works. So that means if there is one least degree 1, that must be the answer. Right? So I'm giving you a somewhat convoluted explanation. So the explanation is this. So the polynomial that I have constructed is the only polynomial of degree less than or equal to k minus 1, which solves that problem. We need to prove this, right? But once we have proved this, it implies that that is the polynomial of least degree which works. So we will address this uniqueness questions next time.
Okay, sir.
Okay.
So any other questions?
So
I
there
think
is no question.
sir. Thank you, sir. Thank you for your
Okay. Yeah. Thank you.
wonderful lecture.
Thanks.
Goswami, sir.
Okay, ma'am. Thank you, sir. So we will meet again coming Saturday.
We will meet on Saturday. We'll meet on Saturday, 6:45. Thanks.
Thank you, sir. Thank you.
Thank you, sir.
participants.
Thank you. Thank you all.
Thank you, sir.
Yeah, thanks.
Thank you, sir. Thank you.